Hello sir, this is Sarthak Sarode and my project topic is implementing Kalman filter algorithm for calibrating sensors in battery management systems, and my teammates are Mirashri and Nivedita R. So in the previous review sir, we gave the detailed explanation about our algorithm as well as our problem statement and deep abstract of our project, like what we are going to do, which softwares we are going to use. So in this review we'll be showing our code that we have written in those C++, whatever outputs we have got, and how we have implemented our project by step. So starting with the problem statement, that our main aim is to implement the Kalman filter algorithm, and this algorithm is used to calibrate the electronic sensors. So electronic sensors are widely used in the industrial applications. If we take any industrial application, we make use of temperature sensor, humidity sensor, position sensor, speed sensor. So all these are electronic sensors, and these sensors take convert physical quantities, that is like physical signals, then it might be temperature, humidity, speed, convert these physical quantities into the electrical ones. While doing so, while converting physical quantity into the electrical one, there are the chances of adding addition of this electrical noise in the system. So this electrical noise can be eliminated by making use of Kalman filter algorithm. So these sensors are interfaced with the microprocessor, and if we write the efficient code for calibrating these sensors, then we can eliminate the noise. So that is the main problem statement of our project, that we have to write the Kalman filter algorithm which makes use of the recursive function. By making use of the recursive function, it eliminates the noise in step by step iterative process. So this is the main aim. And in battery management systems, we have various sensors like current sensor, voltage sensor. These sensors are used to measure the current flowing through the battery as well as voltage present in the battery. So now let's have an overlook on the problem statement in an illustrative way. So as we can see that basically battery management system is like monitoring the health of a battery. That battery management system is used in automotive, electric vehicles, or anywhere in the industrial applications where there is huge scope of electrical components. So these are the current and voltage waveforms. So when we have to measure the current and voltage, we make use of these sensors. So while measuring this unwanted electrical noise is nothing but the ripples in the current waveform or disturbance in the physical signal. So these disturbances get added, and we have to eliminate these disturbances. So what we do, we program these sensors in such a way that this unwanted noise is eliminated, and we get the refined or the purified values of the current and voltage without noise. So coming up to the literature survey, we went through the various research papers of Kalman filter, and we found various algorithms, but the algorithm proposed here is having the minimum computational time, and the time complexity is big O of n square and big O of n cube. So we are defining a one-dimensional Kalman filter algorithm here, and the time complexity is big O of n square. So basically, Kalman filter is having a wide range of applications in object tracking, weather forecasting, load forecasting, automotive vehicle applications, and wherever sensors are used, there is a huge application of Kalman filter algorithm. And this Kalman filter can be implemented in n number of ways. So here we are making use of the technique that is called predict, update, and measurement technique, which has the big O of n square time complexity. So coming up to the Kalman filter code, so this code was implemented in the Dev C++ using C language. So initially we imported the libraries, that is stdio.h, standardlib, and math.h, and we are declaring few variables as well as few arrays. So the input of our code will be nothing but the array containing the input values of the sensors. So now let's assume that in battery management system there will be two arrays like current sensor and voltage sensor, right? So each array will be having continuous values of the sensors. Like if we take an example of current sensor, then continuous values of the current sensors will be present in this array. But for sake of our project, we are taking only n number of iterations, means n number of sensor values. Now the next variable here is ideal. So this ideal array is nothing but the expected values or the ideal values of the array. Then Kalman array. This Kalman array is nothing but the the current iteration values, whereas ideal array was the threshold values. Now then we have two important arrays. First is measured array. Measured array is basically the measured error of the current iteration difference diff measure. So diff measured array is nothing but the difference between the current iteration value as well as the previous iteration value. Then we have the difference Kalman array. So this is nothing but the final array of all the errors there they present in the sensor readings. And finally what we do, we subtract the error values from the expected values and then we get the correct output. So now let's dive in into the main code of the Kalman filter. So initially we took the variables and we declared them as the float, because the data type used here is the float, because the values of the current and voltage are not always integer, because battery discharges in an exponential form. So there is huge possibility of getting the values in the double or float form. So here float k is nothing but the new value, float p is nothing but the covariance, float p temperature is nothing but the temporary covariance value, float x temp estimate is temporary system state estimation, and float x is the actual system state estimation. All these values were explained in the review 1, and basically these are the technical terms of the Kalman filter, and we have certain formulas for implementing Kalman filter algorithms. Those were discussed in the review 1, and these formulas are implemented in the code which are explained in the upcoming slides. So first, before going that, we are taking what the srand1 array, which is initially declared as the 0, and this is the initial measurement of the sensor reading, which is nothing but the system state estimation is equal to the real values of sensor into 0.09. So this is nothing but the Kalman constant. And then we have the some constants, Kalman constants like some error Kalman, some error measure. These are initially declared as 0. Then coming up to the main Kalman filter code, as we can see here the for loop. So this for loop is basically this is the generalized code. So here for loop is run from 0 to n iterations. We can take any number of the iterations. Then as the algorithm was mentioned, algorithm is there are three steps. In first step they predict the values, in second step they measure the values, and in third step they correct the values. So for each state we have certain formulas, like in the prediction state, the current estimation is equal to the n minus 1 into last estimation, and then p temp is nothing but the temporary covariance is equal to the covariance obtained in the last iteration. Then we calculate the Kalman gain. Kalman gain is nothing but the error in the sensor readings, which is nothing but the current iteration versus previous iteration. And then we measure the covariance of the system. This is nothing but the noise. Noise occurred in the sensor values. Then these are some Kalman filter for formulas, like a current estimated state equal to the previous estimated state plus k Kalman filter gain into z measured minus current estimated state. So then these formulas were used for calculating the previous iteration. Then finally we make use of the same formulas just by incrementing by 1 to calculate the current state estimation values. And then the fourth step of our algorithm is nothing but the updating the value. How do we update the value? We simply eliminate the error or subtract the error from the estimated values. Now coming up to the last part of the code, that is nothing but the printing the values. So we are printing basically 5 arrays. First array is of ideal position, second array is of measured position, third array is of difference in the measured position, fourth array is of Kalman filter, Kalman position array is nothing but the error, and then with the important is difference in the Kalman position. And last 2 points are very much important, that is percentage reduction in the error. That means how much percentage of their error is been reduced. So these are certain things. Now coming up to the project outputs. So one thing is significant here is if the number of iterations are less, reduction in the error is less. So as we can see, if we run our code for only 5 iterations, we can see that each array is having the 5 values: first, second, third, fourth, and fifth. So if the number of iterations are 5, there is only 21% of the reduction in the error in sensor readings. So if the number of iterations are 10, we get the 35 percentage of the reduction in the error. If the number of iterations are 15, these were the maximum iterations, we get the reduction in the error, that is the maximum. So if we run the code for more number of iterations, then we get the more number of error. Maximum percentage of error is reduced. Okay, so this is the Kalman filter code, which makes use of the recursive functions and which makes use of the data structures to eliminate the error calculated in the sensor readings. So now I will explain like what is the ideal position, measured position, difference in the measured position, Kalman position, difference in the Kalman position, total error using raw measured, total error using Kalman filter error. So basically, this reduction in the final error, I will just show my Dev C++ code. So these are the three codes. First code is for 15 iterations. We can see that for loop is just a second. This is for 10 iterations. This is for 5 iterations. Uh, for loop is run here for 5 values. We can see this is made to be 5. And if we run now, if I run this five iterations code, then I get the 21 percentage error. If I run 10 iterations code, then I get the 35 percentage error. And when I run the 15 iterations code, I get I get the maximum percentage of the reduction in the error. So basically, these array values are what the values I have taken are the random values I have chosen. What are the possible values a current and voltage sensor can take? Those values I have included. But these values, when we are implementing our project in by making use of hardware components like sensors, then these will be the real time values. Now, the most important thing is like how we are calculating the reduction in the error. So this is nothing but first we calculate the sum error in the measure, then we calculate the sum error in the Kalman error, then we take the division, that is the ratio of both the errors, we multiply it by 100 and then we get the final error. So basically, ideal position is nothing but the previous iteration current values. Measured position is nothing but the current iteration sensor values. Difference in the measured position means current iteration minus previous iteration. Kalman position is nothing but the summation of all the possible values of all the iterations. Difference in the Kalman position is nothing but the error, that is the difference between the all the possible iterations minus previous iterations. And so this is the these are some standard formulas which we took from various research papers, and we implemented these formulas. We made use of data structures, that is array. We stored the values of sensors in an array, and then we have the output of our project is having a array. We have the 5 arrays, like we are calculating the sensor readings as well as the error in an array form only. The each iteration values are stored in the array. So this was the entire project which was done in the Dev C++, that is making use of the C language. Now coming up to the practical part, as I belong to the electrical engineering department, so I did one project that was having the temperature sensor. So I implemented this Kalman filter code in the temperature sensor. I basically made use of Arduino microcontroller, and this is just an application, real-time application of Kalman filter. So as we can see, these are the temperature reading before implementing Kalman filter, and this is the temperature reading after implementing Kalman filter. So as we can see that after implementing Kalman filter, I was getting 24 degree, 24.97 degree Celsius temperature, and before implementing Kalman filter, I was getting 21.97 degree Celsius temperature. And the current temperature at my place, that is in Pune, was 24 degree. So it shows that after implementing Kalman filter, we get the accurate reading of the sensors. And this entire algorithm as well as the C code was explained in the previous slides. Now, this was the code which was given to the microprocessor. So, sensors don't have memory, sensors don't have internal processor to process the code. That's why sensors are just electronic chips which has the internal electrical circuit, basically voltage divider circuit, which uh, takes the physical values and convert them into the electrical signals. So, we make use of microprocessor to program the sensors, and inside the microprocessor we insert the code. So as we can see, these were the Kalman filter gain and the Kalman filter current and previous state values, iterative formulas, and these were some standard coefficients as well as the standard variables of the Kalman filter which were declared previously. And this is nothing but the uh, pin declaration of the sensor. This code was written in the Arduino IDE. So this is the practical implementation of the Kalman filter algorithm. That's it. Thank you.